Lenny Taelman from Amsterdam, a very sought-after speaker in our area, as demonstrated by the attendance, which is more than 70, one of the top numbers we had. So, and he'll tell us about his work on deformations of Calabi-Yau categories.
Thanks a lot, Evgeny. Thank you all for joining in. Please just interrupt to ask questions. Well, it's hard for me to monitor the chat, so just unmute your microphone and say something. Also, please let me know if my handwriting is illegible. It is, with my students, already infamously bad on a blackboard, and it doesn't get better on a tablet. I try to make the best of it, but do ask if something is not clear. Okay, so I want to talk a little bit about, well, let's say deformations of derived categories. So let me gently start with an introduction where I will be somewhat imprecise and vague, but maybe explain how these things occur and why they could be interesting. So what's the context? If I have a, say, smooth projective variety, then I can associate to it is derived category, one of its incarnations. And then, of course, if I deform X, somehow that should mean I'm also deforming the derived category. I put deformation here between quotation marks because there's maybe some foundational questions as to what that means, but let's keep these aside for now. However, in general, in practice, the derived category of X may have more deformations than just those coming from X. It may have deformations that we call non-commutative, that do not come from geometry in a clear way. Let me give two examples of this, maybe two kind of examples. The first is, well, if I have a cubic fourfold, then Sasha has shown how to associate to this a derived category, well, a triangulated category, which is the orthogonal complement of these three, oh, I'm sorry for the scrolling, line bundles, and which is, let's say, a subcategory of the derived category of X. And of course, and it may happen, it does not always happen, that this category is actually the derived category of some K3 surface. Yes, but this is a special condition. And so if I deform X, I will deform AX, but I may lose this property and I may get a deformation which is no longer the derived category of a K3 surface. So that's one such instance. Maybe another example of a very different nature, maybe a very general statement. If X is a general, smooth, and proper variety, then one can consider its second Hochschild cohomology, which, thanks to the Hochschild-Constant-Rosenberg isomorphism, has a very discrete, very concrete description. There's some kind of Hodge-like decomposition, so it's the H2 of X, direct sum H1 X tangent bundle, direct sum H0, and then wedge 2 of the tangent bundle. And then Toda has shown that if you have a class in here, then you can construct to this class a triangulated category, let me call it d gamma of X, which should be thought of as a deformation of d of X. So this is going to be so it's linear over the dual numbers. So there's an explicit construction that does this, and such that it extends the construction that you already know for gamma that lie in the H1 XTX. So this is the space of infinitesimal deformations of X. So such a gamma, to such a gamma you can associate a deformation of X over the dual numbers, and then you can take the derived category of it, and this will be the same as d gamma of X. So here you see these are like the infinitesimal deformations that come from geometry, and then you have extra ones. These ones are easy to understand if you know of twisted derived categories, in the sense of twist by a Brouwer class, because this is some kind of infinitesimal Brouwer group, and these are, well, somewhat more mysterious, but they can be described. So the goal for today is to do something similar as what happens here in Toda's theorem, but not for first order deformations, but for high order deformations, and try to study these things a little bit more systematically. So let me move on to stating the main theorem. And so there is this thing that I actually need to define now what deformations are. And there is a million equivalent ways of doing them, and all of them are somewhat technical. I won't refer back to the precise definition, but I want to have stated one correct definition, at least for completeness, and then I will deal with it more intuitively. So what do we need? So I'll denote by cat R the category of derived categories over R, and more precisely, small pre-triangulated idempotent complete DG categories over R. So let me just give an example. If X over
what is
R.
R?
Sorry?
R is what?
Sorry, at this moment, an arbitrary commutative ring. Thanks. So for example, if X over R is any reasonable scheme, then a DG enhancement of D of X will be such a thing. So I'll just write D of X for that will be an example of such a thing. And I'll denote by Art K, so Artinian K, the category of Artinian local K algebras with residue field K. So the typical example is, so we want to do deformations, maybe to higher orders, or something like KT modulo T to the A. The kind of rings over which you want to do, you want to deform. And then, so to such a category C over K, you can associate a deformation functor, and I'll write down the definition once and then never really use this definition. Namely, you write down the same thing you always write down when you write down a deformation functor. You send R to the set of pairs of a category C tilde and an isomorphism phi, where C tilde is now an R linear DG category, and phi is an equivalence between its base change, and you have to put an L above this just to remind you that you have to be careful in how to define this, but it doesn't really matter now with the original C up to equivalence. And now the what do you say this? The details matter, and so maybe the important thing to make this into a complete definition is to stress that here these two equivalence symbols are meant to mean quasi-equivalence. You can also basically remove all adjectives that I've put in front of DG category and work with Morita equivalence instead, and you get completely equivalent theories. There's several ways of doing this. Precise choice won't matter for now. Okay, then at least I have a definition so I can state a theorem. So here is the theorem. So let C be such a differential graded category, and assume that C is proper and smooth. So I'll very briefly say what this means without spelling it out in detail, but the important thing to know is that if X is a proper smooth variety, then a DG enhancement of its derived category will be smooth and proper. So properness is a finiteness condition. It means that the home spaces between objects, like the derived home spaces, are finite, and smoothness can be characterized as saying that like the diagonal C tensor C op module C is perfect. And you can think about why that is the case in case you come from something smooth and proper in geometry, but it doesn't really matter now. So this is one assumption, and then there is the crucial extra assumption, and I'll put a star in front of it, and that is the following. Assume that the map from the Hochschild cohomology of C, so the action of the Hochschild cohomology of C on the Hochschild homology of C, and I'll say a bit more explicitly what this is in a concrete case in a moment. Assume that this map is injective. So this is now just a technical assumption, and I'll come back to when this holds and what it means in a moment. Then the statement is this deformation functor is pro-representable by a power series ring. And the number of variables is exactly this number of deformations that we had in Toda's result, so it's n being the dimension of HH2. So this is the result I want to talk about today, and let me give a few examples and a little bit of context before diving into why this holds. Let's maybe immediately move to an example of geometric origin. So the main example is if C is dx and x is, so for an x over k, which is smooth and proper, and a Calabi-Yau in the weak sense of the word, so omega x, dimension x is isomorphic to OX, then C satisfies the hypothesis. So that C is smooth and proper is, well, that's how the definitions have been chosen. But let me say something about why the hypothesis holds for the map star over here. So indeed, under these assumptions, you can look again at the Hochschild constant Rosenberg isomorphism, and it will tell you that the D Hochschild homology of C is made up of a combination of various Hodge groups, and there will be only one non-zero. So D is a dimension. Sorry, D is a dimension. There will be only one non-zero group, and that's the H0 x omega dx. And under our assumptions, this is one-dimensional. And then so let me scroll up a little bit. So maybe I'll move up a little bit and then I put the theorem again. So what do we have? So we have the Hochschild cohomology of C, which has some decomposition, as we've seen before, in terms of cohomology of polyvector fields. So this map acts on the Hochschild homology of C. And so if I have, and so I can restrict this action to just looking at its action on HHD. So you restrict to the top degree in Hochschild homology. And then, so the statement is that then it will map HHD to, now let me get the indexing right, let me put the HHD explicitly, so that's H0 x omega d going to HI x omega d minus j. And so there is an obvious map, diagonal map, which comes from the fact that if I have a tangent vector, then I can contract a form and get a form of lower degree with it. So there's an obvious map for multilinear algebra going from this space to this home space. And the statement is that this diagram commutes, so that if I restrict the action to HHD, I get the thing on the bottom. But this map is an isomorphism under our assumption, just because the fact that omega d is trivial shows that, gives you the duality between the tangent vectors and the one forms. And so if this map is an isomorphism, then the top map must be injective, so the condition star is satisfied. So if you want, let's go back to the statement now. The condition star is some kind of Calabi-Yau-like condition, but it's a rather weak Calabi-Yau-like condition. It holds in all Calabi-Yau-like settings, but also in certain other settings. Okay, let me pause here for a moment. So let me, for comparison, recall.
Lenny.
Yes.
Just to be sure, you want injectivity on the entire cohomology, not only on the second cohomology, right?
Yes, absolutely, in every degree, and this will be usually used.
And
yes.
Is it important?
It is very important, yes. So this will be a theme in the rest of the talk. Is that the statement is somehow a classical statement involving only an HH2, at least in its conclusion, in classical deformation theory. But the proof somehow goes through more derived mechanisms that really need statements in every degree. So I think this will become clear later on.
Okay, good. Thanks.
Can I ask, in the deformations, there's no flatness assumption over the base?
No, so this is again a dependent choice on how you set it up. You can either put in the flatness condition and then change your notion of equivalence, or you can allow enough. So under quasi-equivalence, you will have a flat replacement, and then it will still be represented by this functor. So there's several equivalent ways of setting up this functor.
Sorry, last thing, Lenny, where you put n equals the dimension of HH, and is that a Q or a 2?
That's a 2, absolutely. Sorry.
That's a 2. Okay, thank you.
Address this. Yes. So maybe let me come back to this in the next remark. So there is also, of course, the Bogomolov-Tian-Todorov theorem that says if X has trivial canonical bundle, so for an X as above, then the deformations of X are pro-represented by a power series ring. But now with M, the dimension of H1x Tx, which is less than or equal to n because it's a subspace of the HH2. So this reflects what I showed earlier in Toda's construction.
And this holds without any extra assumption, right?
Yes. But also, so the assumptions here are weaker than here. So the assumption here is only some injectivity on this map on Hochschild cohomology, whereas so which is implied by having trivial canonical bundle, but it also holds in other cases.
Is there any example where the two deformations have a singular base space, but the derived deformations have a smooth one?
I do not know. It is not a priori impossible. I really do not know. Okay, so let me move on now to, well, how do you prove such a thing? And I've already hinted a little bit that more derived or homotopical methods will come into play. So I want to somehow give a really very short bird's eye overview of derived deformation theory. And there's many languages in which you can do that, but I'll follow closely. So this is a theory that has been developed by Pritham and Lurie and others, and I'll follow closely the language of Lurie in this. And I really will be very brief on this, and it's maybe mostly seen as an advertisement. If you like deformation, when I saw this advertisement and I like deformation theory, I knew I wanted to learn more about this. And then I'll also show how one can use it. So the one-line summary is, we'll consider deformations not only over Artinian rings, but over Artinian commutative differential graded algebras. So what does that mean? Well, a commutative differential graded algebra, so a commutative algebra in the category of chain complexes, is called Artinian if, well, first of all, it has cohomology only in a non-positive degree. This is an artifact of sticking to cohomological degree conventions here. Its total cohomology is finite dimensional, so it is finite length in a certain sense. And then H0, which is itself a commutative ring, is Artinian in our sense. So it's a local ring of finite length with residue field K. So it's some kind of homotopical thickening of a usual Artinian algebra. And then very loosely speaking, a formal moduli problem. So that's a deformation functor in this context. So what is it? So I'm going to make many small lies now. So it's a functor F underline, and I will use underline every time I do something derived. So this will be a convention throughout this talk, from this category so of Artinian DG algebras to the category of spaces. That satisfies, well, two conditions. The first is it maps quasi-isomorphisms to weak homotopy equivalences. So quasi-isomorphism of commutative differential graded algebras is just a map of differential graded algebras that is a quasi-isomorphism as a map of chain complexes. So this somehow says that this functor is homotopically meaningful, that that's all I want to say about it. And second is it satisfies, and I will not spell this out, some derived version of the Schlessinger axioms. Right? If you do normal deformation theory, you consider functors from Artinian rings to sets that satisfy a list of technical axioms. Without these technical axioms, you can't do anything. And here you have a very analogous list of technical axioms. Actually, they're more elegant than the non-derived versions. And this is the definition.
Is it a functor or two functor or infinity functor?
So it's better to say an infinity functor. Yes, absolutely. And so the main thing I want to stress for now is that such a formal moduli problem, it induces a deformation problem in the classical sense. So it's kind of a lift of a deformation problem, F from normal Artinian rings to sets well, if I have an Artinian ring, then I can see it as a differential graded Artinian ring by putting it in degree 0, and then I can apply my F, and then I get a topological space, and then if I have a space, I can take its pi 0, its connected components, and I get a set. Okay, and so the derived Schlessinger actions are set up in such a way that this thing will satisfy the Schlessinger actions if the original ones satisfied the derived ones. And so so here is a fact of life, or an observation, is that most, if not all, most F in nature have a natural lift, have a natural thickening to some F underline. And in many ways, so one way in which this is often used, and was actually already used before the whole theory was around, is that in many ways the F underline is a more flexible theory. It is more easy to manipulate. And this is something that we'll do also in this talk.
Is it important that you consider only commutative DG algebras?
Yes and no. I'll come back to this question in half an hour. For now, I'm considering only commutative ones.
Sorry, can I ask a question? Is there notion of tangent space to the deformation function?
Coming up.
Setting and obstruction and all that?
Coming up right away.
Okay, thanks.
So let me first state the main theorem about these things, and that's the theorem of Pridham and then later Lurie, which states that there is an equivalence of categories. So there is a very nice classification of formal moduli problems, namely, let me call this equivalence Lie, so that's the name of the functor. A formal moduli problem is equivalent to the datum of a differential graded Lie algebra. So a Lie algebra in the category of chain complexes. And this already shows that the theory is much nicer than the usual theory of deformation problems, because there's no hope of any such classification. And let me give an example of this rather than going in detail into how this is constructed, and then also come back to the question about obstruction and tangent, etc. So here is the easiest example. So maybe not the easiest. Here is an intuitive example. Let me put it this way. So let X be a nice variety and E a vector bundle on X. Then you can consider the problem of deforming the vector bundle on X. So keep X fixed and try to deform it. So this lifts in a very natural way. You think about it and you write down the only meaningful definition, and that will be your canonical lift to such a formal moduli problem. So it lifts to a formal moduli problem. And so there is an associated Lie algebra. And this Lie algebra, I can tell you exactly what it is, almost exactly. Namely, you take the derived endomorphisms of E. Maybe let's first do it as a sheaf, and then take global sections. So this thing. So this thing is a Lie algebra using the commutator brackets, and it's endomorphisms of a thing. And so the global sections of this will, if you set up things correctly, again be a Lie algebra in the category of chain complexes. So this will define a DG Lie algebra.
Don't you need to shift by one?
No. There will be a shift by one later, but there's no shift by one here. And this is the differential graded Lie algebra, and it should be this one, right? Because in degree 0, it really is a Lie algebra by doing the commutator of endomorphisms. There will be shift by one coming up though. And so this should look familiar, right? Because if I take the HI of this Lie algebra, then in this case I get the XI EE, and these things, they play an important role in deformation theory of vector bundles. And so one of the nice things that this theory does do is that So these things, they play an important role in the deformation theory of vector bundles, but essentially only I equals 0, 1, and 2. Like 0 gives you infinitesimal automorphisms, and 1 gives you the tangent space, and 2 an obstruction space. And this theory somehow gives a completely uniform treatment of this for all I, and in fact for all integer I. So it doesn't see this distinction anymore. This becomes a meaningful and interesting thing for every integer I.
I'm sorry, I must have missed it. Is K characteristic 0 from the get-go?
Yes.
Okay, cool, thank you.
Yeah. Yeah, absolutely. And I guess this theorem is the first place where I really use this.
Yeah, good.
And so maybe let me also make a comment about it. A surprising amount of what I will say actually holds in characteristic P, but not everything. Maybe I'll say something about it at the end. Let's stick to this now. Okay, so this was my super short bird's eye overview. Now let's move to deformations of categories and to actually what the problem is.
In the example, you didn't really care that it was a vector bundle.
No, and any perfect complex on something proper would have worked, I think. I presume that was what your question was referring to.
Exactly, thank you.
Okay. Okay, so now instead of taking a vector bundle, we take a differential graded category. And I won't write out the definition, it's actually a bit of work to do, but there's a completely natural infinity functor, def underline C, that associates to a differential graded algebra the space of lifts of your differential graded algebra to that thing. And now the main problem in this entire talk, the main reason why it is not easy to obtain the theorem that I gave you, is that this thing is basically never or almost never a formal moduli problem. Maybe I should be more precise. It's almost never known to be a formal moduli problem, and it's known in some cases not to be one. And this is what basically kills all hope to naively apply your standard techniques to show that something is unobstructed, that something is representable by a power series ring. It is, well, if you don't have something that satisfies the Schlessinger axioms, you cannot use your standard tools. However, the theory of formal moduli problems is very flexible, and one of the nice things it does is it has an operation that I mean, it's not called that, but let me, for intuition, call it that way, that I like to call formal moduli problemification. If something is not a sheaf, but only a pre-sheaf, you make it into a sheaf. And you can do the same thing here. So this functor has a canonical map, a universal map to something that I put a hat on top of that is a formal moduli problem. So this thing will now be a formal moduli problem.
So can you say more precisely what is missing without this formalization? Or?
That's coming up. Yes. I mean, this is the nature of the problem of dealing with these things. Yes. So let me first give you the main theorem about this, which is due to Lurie. And it consists of two parts. So first of all, well, the thing on the right is a formal moduli problem, so there's a Lie algebra associated to it. And you can at least say what the cohomology groups of this Lie algebra are. So the HI of Lie of this associated formal moduli problem is canonically isomorphic to the I plus first cohomology, Hochschild cohomology of C. This was maybe the shift that Sasha was expecting earlier, at least a form of it. Now, if you know more about Hochschild cohomology, you would say, oh, okay, so actually this Lie algebra is just the Gerstenhaber Lie algebra on Hochschild cochains. This is actually not, this is without doubt true, but not so clear that one can easily prove this. So one of the things we'll have to do is avoid trying to use this. And so the second statement is that under some mild finiteness assumptions that I won't state, but that will hold in our cases, for every R, the map from pi 0 of the original thing to its associated formal moduli problem is injective. So the statement is saying that, well, you would expect deformations of your category somehow to be related to Hochschild cohomology. And so there is a deformation theory that is related to Hochschild cohomology, but there may not be enough actual deformations of your category. So this is a subset, and some of these classes here may not be realizable by something on the left, and in general are not. And so let me recall. So this is what we called the def CR, the set without the underline thing. And let me then denote this thing by a head. So we have an injective map here. So I'll use this notation later. So the game will be somehow to play one against the other, to use that this thing satisfies all the actions you want and you can work with it. This is the thing you are interested in and you actually want to prove something about, and you'll have to play one against the other to obtain results. So then there is another important theorem that says that in certain cases we know more. And so this is a theorem due to Blanc, Katsarkov, and Pandit. And I'll modestly put a small plus epsilon because there's a small extension of this theorem. And the theorem says that if R is a power series ring in a number of variables, then this map actually becomes a bijection, is actually surjective. So let me stress, is a bijection. Okay, and I will not talk about this at all. So this is a completely different kind of mathematics than the rest of the talk. This is really uses the full force of Lewis machinery. It really crucially uses that you can extend this deformation problem from commutative algebras to algebras over the little disk opera. So almost commutative algebras in some sense. So it's a highly homotopical in nature. I just want to say that the crucial input to make the argument of these three people work is that K is a perfect R module. So in the paper, this is done for a power series ring in one variable, but really the only thing that is needed to make the argument work is that the residue field is a perfect module. And that, of course, obviously also holds for a power series ring in several variables. And then you already, so the argument completely breaks down if you try to do this to show for an arbitrary Artinian ring that this is going to be a bijection, and it's very far from being perfect. So that's all I want to say about, so this is somehow the general theory of deformations of DG categories, the main theorems that we will use in there.
But I'm sorry, is it meaningful to substitute R into this deformation functor? R is not Artinian, right?
Very good question. So a priori, no. But there is a somehow canonical extension. And so what you do is, so now you have to be careful. You take the homotopy limit over all the Artinian quotients of R, over all the truncations. And that is the way you define, that's how you define the extension of your infinity functor to also pro-Artinian rings. So there's a canonical way of doing this.
So it is secretly defined on pro-Artinian rings, right?
Yes. And I'll swipe this under the rug in everything that follows, but you do need to do some work there.
Mm-hmm.
Okay, so then now comes the main new ingredient, and I'll be talking for a while without writing, and that is there is a period map that makes the argument work, and I want to talk a little bit about the classical period mapping in classical deformation theory first to set up the analogy so that I can somewhat quickly move to this kind of more derived version. So assume we have a smooth and a proper variety. Then to this we can associate, well, there's three things that will matter to us. So we have its algebraic de Rham cohomology, and on the de Rham cohomology we have the Hodge filtration, and then we have the Hodge to de Rham spectral sequence that relates these things. So for example, it tells you that the Hn de Rham is non-canonically isomorphic to this direct sum. It's kind of Hodge decomposition. And the kth part of the Hodge filtration is then the submodule consisting of these parts where P is at least K. So this is the general form of this thing. And the main thing that matters to us is that, well, is the Gauss-Manin connection, or there's many shapes in which it's known, which essentially says that this thing, the algebraic de Rham cohomology, well, let me say, is a topological invariant, is topological or is horizontal or is constant. I'm not so sure how to say this. So it doesn't move in families. Of course, because the de Rham cohomology, if you want, by the de Rham theorem, is a purely topological invariant. So this doesn't move in families, but of course, the Hodge filtration on it moves when you deform things. And these are the ingredients you need to build a period map. So what do? So let me first spell this out in a different way. The fact that H de Rham doesn't move in deformations means or is equivalent with the statement that if I have a lift of X to an Artinian ring, then its H de Rham cohomology can be canonically identified with the Rham cohomology of a special fiber tensored to R. It's one instance of this not moving in families. So how can you use this? Well, now, if I have a deformation of X, and I can associate with the deformation of my filtration of the Rham cohomology, right? By sending X tilde to the filtration on the Rham cohomology of X tilde, which is just the original thing. So you can, well, not spell this out, so you can define a deformation functor of this kind, and then you'll have a map of deformation functors from one to the other. And it is some kind of local version of the usual period map. If you deform your variety, then you move the Hodge structure on cohomology. That's all I'm saying in a somewhat more algebraic setup than maybe the classical complex picture gives you. Questions about this setup? Because I now will quickly scroll to a somewhat much more abstract setup.
Is Hodge filtration flat in general?
Well, so on a smooth and proper thing, it will always be locally free. It is not, if that is what you mean.
I mean, of course, it is fine for a variety, but if you consider a general category, is the dimension of Hodge filtration constant in smooth and proper?
This question for a moment, because we are not at the general category yet, and we'll be on the next page, if that's okay with you. So now we want to do something similar for a smooth and proper DG category, and I will need smooth and proper. So maybe the answer to Sasha's question is definitely in general no. And then we have a completely analogous picture. Through very different kinds of homology theories that were developed by Alain Kohn and then later many others. So to such a DG category, you can associate its periodic cyclic homology. Let me for now only say that it's a DG KU inverse module, where U is a variable in cohomological degree 2. And so because I also have its inverse, it gives some periodicity. So periodic cyclic homology in degree in all even degrees is the same, and in all odd degrees is the same. It's periodic modulo 2. And there is also negative cyclic homology, which is similarly a module over dg over KU. And there is a spectral sequence, which is sometimes called a non-commutative Hodge to the Rham spectral sequence, which was proven to by Kaledian, which relates the Hochschild homology of your DG category to the periodic cyclic homology. And you really want you to think of these three things as analogs of what I had before. The Rham cohomology, Hodge filtration, and the Hodge to the Rham spectral sequence. That's how we will use them. And let me maybe spell this out a little bit. So for example, this spectral sequence, it will imply that the end periodic cyclic homology of C has a direct sum overall. I hope I don't mess up the indexing. P minus 2i equals n of the Pete Hochschild homology. And then let me just put a formal variable in here times u to the I. So that the formal variable will bookkeep how the action of u on this whole graded space will act. So this is under this smooth and proper condition, right? Under this spectral sequence condition. And then there is then the negative cyclic homology will form a subspace, and it will be the sum of the same things, but now with the condition that I should be at least 0 of the same things.
So does the spectral sequence degenerate in this case? Is it the claim?
Yes. Oh, so this. So maybe I should not have said the Kaledian spectral sequence, but the theorem of Kaledian is that the spectral sequence degenerates. Thanks. Yes. And so it's under this degeneration that you get these non-canonical identifications that I've given here. And maybe I will not spell this out because there's a mess of indexing that only confuses. But the important thing to know is that if you apply this to see the derived category of a smooth and proper variety X, then periodic cyclic homology will give you the Rham cohomology made periodic. So you only see the index modulo, the degree modulo 2. And this negative cyclic homology will contain exactly the same information as the entire Hodge filtration. So you can recover the Ramco homology with its Hodge filtration from this thing. But it looks a bit weird because it's made periodic in some way. So now there is a theorem which maybe is a version of a theorem due to Goodwillie, which says that, well, this periodic cyclic homology, if you want, is a topological thing again. It doesn't move in families. So the precise statement is HPN of some lift can be canonically identified with HPN of the special fiber tensored up with R. So it's some kind of Gauss-Manin connection thing again. So this now gives us all the tools that we want, that we need to build a period map. So I will now denote by period C, the period domain that we need, and I'll define it informally. So what is it? It is the space of deformations of the, well, so what happens now is that, okay, let me spell it out, the KU lattice negative cyclic homology in the KU inverse module, which is periodic cyclic homology. So let me say maybe in the fixed between quotation marks. So we have a fixed module and in there a submodule, a lattice that moves, and so you get some kind of Grassmannian, but in a very derived sense, we have to do this over arbitrary differential graded Artinian rings. Okay, and now the entire point of the story is that because of Goodwillie's theorem, you get a natural transformation from deformations of C to the period domain by sending, maybe I put it above, by sending some deformation to the lattice, which is going to be the negative cyclic homology, which will live inside the periodic homology, which we can identify with the fixed thing. So we get a period map of this kind almost for free. And now now I'm cheating a little bit, but forgive me the cheating. Because this thing is a formal moduli problem, it will factor over our formal moduli problemification. So we get a factorization of this kind. Okay. Let me scroll back for a little bit. So this was a lot to take in if you're not used to these things. But what we've done is, by following the analogy with variation of Hodge structure, we've set up a period map from deformations of a DG category to some kind of period domain.
Sorry, just how are you cheating? That seemed totally legitimate. Of course, some kind of sheafification should be functorial.
Yeah, so I'm cheating because actually you do need to do work to show that this is a formal modular problemification, and it is actually better to just avoid this work. But
oh, okay, thank you.
So no, there is. So the honest answer is no, it is not cheating. It is just not the way it is done. Let's say in the upcoming paper, that's maybe the way. What the honest answer is. Okay. So now comes the theorem. Maybe I should also stress, of course, that I mean, there's nothing new here in IDs, right? This whole theory of cyclic and periodic homology is developed to do exactly these things and has been used for great length to do some kind of Hodge theory for well, non-commutative things. So now here is the main theorem that we need to prove our main result, and which is a theorem about this period domain. So it consists of two parts. The first thing is that, well, the corresponding Lie algebra, so that's a differential graded Lie algebra, and it is abelian. So it has trivial bracket, or is quasi-isomorphic to something with a trivial bracket. It's only defined up to quasi-isomorphism anyway. It's abelian. And well, if it's abelian, then it's essentially just a DG module, but it's a DG module over a vector space, over a field. So basically, if we know its cohomology groups, then we know everything about it. And so I'll also tell you what the cohomology groups are, namely the ith cohomology group. And I'll just put a dot, and I'm sure I will mess up a shift now. So the cohomology of this is you take so this is all under the assumption of smooth and proper. It heavily uses the degeneration of the spectral sequence. So you take the endomorphisms of the Hochschild homology of C, and so that's a finite dimensional K vector space. You tensor it up with this quotient, so there's going to be a long formula, and you put a shift by -1. Okay, long formula, but it's not so strange if you think about what I've written before, and if you think that this period domain is some kind of Grassmannian, and if you think about what the tangent space to a Grassmannian looks like, it's somehow the expected formula if you work out what is written above. And maybe I should also say now the fact that some DG Lie algebra corresponding to a deformation problem is abelian really means that this deformation problem is unobstructed. And in that sense, this is also not unexpected, because if this thing is a Grassmannian, it should be smooth. So this is somehow, the statement is saying this derived Grassmannian is smooth and its tangent space is what you expect it to be. Now, so then the second statement is, well,
so this abelian is very confusing, right? Because the Lie algebra is not, I mean, the bracket is not trivial, right?
Well, so the bracket is trivial.
I mean, this is JLN, no?
No, so this is the, no. So really, so let me stress this. It's really this thing as a differential graded vector space, but with trivial brackets. And so it is. So let me say something about it in a moment. So
but this is somehow contradictory to what you said before, that this is something like Grassmannian, right?
No. So okay. Now you're tempting me to give the proof, because the proof is quite nice. Okay, let me quickly sketch the proof now. Then I will regret this. So the proof is the following. This period domain is actually the homotopy fiber. So there's some kind of fiber sequence of, you look at deformations of negative cyclic homology. And if I have and these induce, so by maybe tensoring, by inverting U deformations of periodic cyclic homology. So there is some kind of homotopy fiber sequence, and this thing is classified by some GLN, namely the Lie algebra, which is the endomorphisms of HP. And this thing is classified by the Lie algebra, which is the endomorphisms of HN. But the homotopy fiber of this thing is some complicated thing, and so it's the wrong. How shall I say? This is like an injective map of Lie algebras, of which you want to take the kernel, and so that's what accounts for the shift. And so if you compute this homotopy fiber in the category of differential graded Lie algebras, that's what I want to say. You get this abelian differential graded Lie algebra. So it comes from objects that are GLNs, but the thing itself is not. Maybe now is not the time to try to spell this out in detail. I realize. So it is absolutely related to a GLN, but it's a trivial Lie algebra. So, and this will be crucial. And so the second statement is we had this map here, our period map, and that so it gives an induced map on Lie algebras, and we can say exactly what it is. And this is maybe the technical core of the whole argument. This is maybe the only place where something non-trivial happens. So you can look at the deformations of C and then the associated form of moduli problems, and you have an induced map to the Lie algebra of your period domain, and you can say exactly what it is. And so what is it? So this thing we had seen is the same as the Hochschild cohomology up to a shift, and this thing. And so I'll tell you what it is. So the Hochschild cohomology maps, acts on the Hochschild homology. That gives me a map of differential graded vector spaces, or of graded vector spaces, to this thing. And then I'm going to put a U inverse and a shift by -1. And this is some sub-graded vector space of the thing above. So what I'm saying is, so this is the map coming from the period map. This is somehow the natural map coming from the action of Hochschild cohomology and Hochschild homology, and I'm saying that the diagram commutes. And this is, I mean, philosophically, this is some kind of Kodaira's, I mean, I'll write it down, Kodaira-Spencer statement saying that if you deform your derived category, then the resulting deformation of the Hodge structure is the one you expect it to be. Okay, that leaves me with, maybe I'll leave this on for a moment and ask if there are questions about this. If you were confused by all the periodic homology, etc., come back. We'll only use this in a purely formal way now. So now I'll go to the proof of the main theorem, and it will be, I mean, we'll use 2 black boxes, but otherwise it should be a rather intuitive proof that doesn't use much. The argument is actually surprisingly simple now.
Sorry, can I ask a little question?
Please do.
The homology you're using on graded differential Lie algebras is the homology I'm expecting for the differential?
Yes. So it's the cohomology of the underlying chain complex.
Okay, thank you.
Okay, so then we come to the proof of the main theorem, and I've repeated here the main theorem and the 2 ingredients that I discussed in the past 40 minutes or so. So what's the theorem? We have a smooth and proper DG category satisfying this kind of injectivity condition, which is satisfied in all Calabi-Yau-like settings. So then the claim is that the deformation functor, the naive set theoretical one, is pro-representable by a power series ring. I should also say, so it's n being the dimension of the second Hochschild cohomology. So, and what do we know? We know that, well, so the main problem in proving this is that this thing is, well, I didn't say this explicitly, but I should say, is just like the derived thing is not a formal moduli problem, this thing does not satisfy the Schlessinger axioms. Not a priori, of course, after you've proven the theorem, it does satisfy it because it's pro-represented by a power series rings. It's nice as it could get, but you do not know that it satisfies the Schlessinger axioms. But we have an associated thing that does satisfy the axioms, and we know that for every Artinian algebra, this map is injective, and that for a power series ring, it is bijective. Okay, and the other thing we know is that we have such a map of formal moduli problems, a period map, where the target has abelian differential graded Lie algebra, and on the cohomology, we have a completely explicit description of the map, and it's somewhat related to the map up there. Okay, so this is all we need to prove the theorem. Maybe. So the first thing we'll do, I think I'll be able to finish this in time, is to note that our assumption star is an injectivity assumption. Well, okay, I'll try not to scroll too much, scroll back once. So this map is exactly the map that occurred in our Kodaira-Spencer map here that described well, the effect of the period map on the cohomology. And so what we conclude from this is, so star implies that the map from the Lie algebra of our associated formal moduli problem to the Lie algebra of the period domain is, well, I'll say injective on cohomology. Right? For every I, it induces an injective map on cohomology. Because that's exactly the way we've defined the assumption star. But if I have a map of chain complexes over a field, and now we usually use the work over a field that's injective on cohomology, then that really means that this map has a splitting as a map of chain complexes over a field. So, well, after passing to quasi-isomorphic things, but it's quite that another work. So this implies that the map, it implies that there is a splitting S, so let me call it S, in the category of DGK modules, but of course not respecting the Lie algebra structure. Okay, but now we can consider the following map. So now I can look at this map, deformation C. So we have our map to the Lie algebra of the period domain. And then I can post-compose with the splitting. But so this thing had a trivial Lie bracket. So if I if I take this Lie algebra again, and now I make it in a new Lie algebra by killing the Lie bracket, by setting the Lie bracket equal to 0, then the second map is actually a map of differential graded Lie algebras, because this one also had a trivial Lie bracket. Right? And so what is this map? This map now is a quasi-iso of differential graded Lie algebras. But the thing on the right has trivial brackets, so we conclude that this Lie algebra actually is abelian, or is quasi-isomorphic to an abelian Lie algebra.
But I guess the cohomology of a differential graded Lie algebra also has some higher operations, not just bracket.
Absolutely. So you have to make this argument work. You have to be careful.
So when you say that this Lie algebra of period functor is abelian, you mean that all higher operations are 0?
Okay. So now I understand the question. What I mean is that there's different ways of setting up the theory of differential graded Lie algebras. And they are all like homotopically equivalent. And the easiest one is just saying a differential graded Lie algebra really is a strict Lie algebra in the category of chain modules, and then there are no higher operations. There's just a differential and a bracket. And you can also, there's variants where you do L-infinity algebras and you have higher operations, but they give equivalent theories, and I won't consider them here.
Yes, I understand, but I think your statement about abelian property was only about cohomology of this.
No. So the statement really was that the Lie algebra is
itself
abelian, and I gave a description of, moreover, of its cohomology.
But is it abelian on the nose, or is it like?
It's the way I set it up. It's only defined up to quasi-isomorphism. Yes. So I see where you're coming from, but there's other approaches to using differential graded Lie algebras in deformation theory, where you actually construct genuinely well-defined differential graded Lie algebras, and then the question becomes meaningful whether it's abelian on the nose or only up to quasi-isomorphism. But in this theory, all these things are only defined up to homotopy equivalence, and so this differential graded Lie algebra is not really a well-defined thing in the one categorical sense of the word. So I'm really being sloppy there, but the statement I state here is correct. And the statement itself is not sloppy. Let me stress this. So this thing is abelian. So the second part of the proof now is the fact that it is abelian has an immediate consequence, and that somehow follows from the theory quite easily, namely that this functor is what we want it to be. So it's pro-representable by a power series ring. Oh, sorry, now I have to be careful. Now I remove the underline, so I take the pi 0 with the correct number of variables. So this is a general statement about formal moduli problems with abelian differential graded Lie algebra. This has nothing to do with deformations of categories. So we're almost done. So it suffices now to show.
And this is def, which is not underlined, and this is by definition a problem that corresponds to this trivial Lie algebra.
So the not underlined means taking the pi 0 of the one, so meaning taking just the set theoretical one, just to strict to ordinary Artinian algebras. So maybe let me actually.
But do you mean that it is somehow related to the Lie algebra with 0 bracket?
I'll come back to that in a moment. Just a second, let me now write this. So this is now just the classical functor, right? And the statement is this one is pro-representable by this thing. And so this is a general statement. If I have a formal moduli problem whose differential graded Lie algebra is abelian, for example, this formal moduli problem, we've just shown that its differential graded Lie algebra is abelian, then the associated, I mean, there's a more general statement, but the associated deformation functor is pro-representable with a number of variables, and the number of variables is the dimension of the H1 of the Lie algebra. So now that we have that, so it suffices now to show that the map, that for every Artinian ring, this map, sorry, without the head. So we know that we have this injective map, and if we can show it is also surjective, then we are done. Okay, now, sorry for going perhaps 1 minute over time, but bear with me, we're essentially done. And the proof of this now is a one-line trick. So let's consider our associated functor, and let's assume we have an element in here. And so we want to show that it comes from an element in here, right? But our functor is pro-representable. So this x, it lifts, it comes from a universal element in over this power series ring. So there is a universal element there, and then there is a map like fx depending on x from the power series ring to R that maps the universal element to this x, that is saying what it means to be pro-representable, to have a universal object. But we've seen that for power series rings, this map is perfectly bijective. So here we have the power series ring again, and now we are done. If this diagram commutes and this map is surjective, then this map, well, sorry, so then x has to be in the image of this thing, is what I'm saying. So we conclude x is in the image of, we call it theta, and well, we took an arbitrary x, so we see that theta is a bijection, and so therefore there is no difference between the deformation functor and its associated one, and we just saw that the associated one was pro-representable by a power series ring. Sorry for going over time. Thank you for your attention.
Okay, thank you very much, Lenny, for this wonderful talk. Any questions to Lenny?
Sorry, just to not let it, not so I don't forget it. First of all, thank you for the talk. And could you give me a hint of why we needed this hatting? Like just a hint of an example of what's a DG category which have these deformations that can't be patched together in the Schlessinger-Schieffi way to another.
Okay, so here the answer is going to be rather unsatisfactory. So there's very easy examples where you take the DG category of, say, DG modules over a Laurent series ring. So KT T inverse, where you put T in any non-zero, I guess degree 2 is the standard example, in a non-zero homological degree. And then it's actually, I think, so this was so this has come back in many ways. So let me give a bit longer answer. So it was observed by, I think, Bernard Keller and maybe Wendy Lowen, that there are examples of things that should, from what you expect from Hochschild cohomology, arise from deformations of your DG category, but where the DG category cannot exist. So in their language, it's also related to what is called the curvature problem. If you have a differential graded algebra, then the Hochschild cohomology should give its deformations. But if you write out the deformations, you will actually get deformed differential graded algebras that are curved, in which d squared does not equal 0 anymore. And so the question as to what is the image of this map theta is maybe the question as to when is such a curved algebra Morita equivalent, whatever that means, to an uncurved one. This is not the language in which Lurie does this, but it's at least philosophically the same problem.
I see. Thank you. And you mentioned you might want to say a hint about characteristic P. Like, suppose you start in the easy case where I give you a lift of everything compatibly to the second bit vectors. Do you hope that things just work? And
to be honest, yeah. So most parts of the argument seem to work, including even so Goodwheeler's theorem, for example, does not hold in a characteristic 0, but the form I need of it, and actually that one needs to reprove in this setting because you need to extract more information from it to get the Kodaira-Spencer thing, seems to work in characteristic P. And this last argument seems to be quite formal. So it is plausible, but this is really guessing, that one can make this argument work using the theory of partition, the algebras of Brandner and Matteo, but this is really, I'm not a homotopy theorist, so this is really not at all obvious to pull off for me at this stage.
So you mean rather than working with DG setup, you work with the Matthew Morrow setup of different rings, right?
Sorry, say again?
You don't want to work with DG rings in positive characters.
Yeah, so you have to choose also over which kind of derived rings you're going to work. But that, I mean, the argument seems to be rather agnostic to that, so that should not be such a problem.
Oh, but you mentioned that you wanted to say something about hyperkahers.
Yeah, so I didn't say this. So there, I guess I promised more in the abstract. So the reason I care about this is that you can apply this to, say, a Calabi-Yau variety. Now there's three kinds of Calabi-Yau varieties. There's the strict ones. For the strict ones, this is completely an interesting theorem because there the HH2 only consists of H1TX. So there all the non-commutative deformations actually are commutative. So it gives you nothing new. But for abelian varieties and for hyperkahler varieties, actually, it does give you new things. And one of the other things I can show is that in these cases, you can refine this period map into a period, so with a bit of Lie theory, into a period map that's actually a local isomorphism. So it shows some kind of local Torelli theorem for deformations for derived deformations of hyperkahlers and abelian varieties. And the result is extremely suggestive. It really also suggests what a global moduli space, there's many problems with that, or such things should look like.
Sorry, just so I can catch up, can you say that there exists a global moduli space and know that it's smooth, but not yet be able to prove properties?
Okay, so you can write down, how do you call it? A period domain, a global period domain, and write down a set theoretical map from deformations of, say, the derived category of a hyperkahler variety to that global period domain, and show it is well defined. And then there's all kinds of hints that it should be essentially injective. And this theorem will tell you that it's also at least locally an isomorphism, that it's really kind of local Torelli theorem. But to say anything more structural about that, there's many problems in trying to make this into a more structural theorem.
Sorry, by locally you mean after passing to the completion, or does Artin approximation work fine and you got like?
No, I really mean after passing to the completion. Really, it's completely a formal statement here.
So when if you apply this thing that you just said to K3 surfaces, this global period domain that you get, would that be the sort of period domain for cubic fourfolds, or?
It's slightly larger, so it would be the domain of K3-like Hodge structures on the Mukai lattice. So okay, now that you ask cubic fourfolds, so if you actually want to prove anything serious of what the speculation I just said, I mean, to have good moduli spaces already in algebraic geometry, you need polarizations, right? And there were no polarizations in this talk. And so the analog of polarizations here would be stability conditions. So you would need to do the whole, so you would need to have a good theory of stability conditions for the objects you consider. Even an existence statement can be problematic. And then you would need to do the whole deformation theory again, also in some kind of stabilized setting. It might be that it's easier, but I mean, there's many problems to do this. But so having done all that, I guess the answer is you get a period domain of dimension 1 larger than the modular space of cubic hypersurfaces, of cubic fourfolds. So there's K3 surfaces, then there's cubic fourfolds, it's 1 dimension more, and then there's this kind of non-commutative deformations with some stability condition. But I really hope, I should double check.
And it seems, if I understand correctly, your main theorem has much weaker assumptions than Calabi-Yau property, right?
Yes.
Does it work, for instance, for fractional Calabi-Yau categories?
No idea. I should check.
And maybe if you have a category which has a semi-orthogonal decomposition with all components being Calabi-Yau of different dimensions?
No idea.
I mean, kind of deforming the gluing by module should be a simple thing, right?
I would not be surprised, but I really don't dare to make a guess at this stage. I mean, and in the same line, I should also say, so in a completely, maybe from a bit of a different field of mathematics, there's a huge supply of what is called Calabi-Yau differential graded algebras, coming from constructions, more from representation theories. And the theorem applies to all of these things. And it would be interesting to see if there are such areas where you get.
But they're typically not smooth and proper, right?
Yeah, I guess yeah. So it's difficult to construct them smooth and proper, but there exist such examples. And what I do not know, I have no feeling for, is that there exist such examples where this phenomenon that look like K3 surface and not like strict Calabi-Yaus, meaning that there are deformations of the derived category that you did not already see in geometry in a cheap way.
Probably those representation theory examples, if you put some equivariance, it might be close enough to proper that maybe something works. I'm not sure.
I'll be happy to hear more about that.
But I mean, do you have natural examples where your assumptions hold, other than weak Calabi-Yau varieties?
No, I mean, so you can construct artificial ones, but I have not encountered a natural example, no. And the artificial ones is, it quite often happens that that Hochschild cohomology is tiny and Hochschild homology is not, and then it's easy for this map to be injective.
So how shall we think about these deformations of these derived categories of abelian varieties? Is there some analog for this K3 surface case?
What do you mean?
Like for K3 surface, you said that if you deform this derived category of a K3 surface, you should think about it as some sort of Kuznetsov component.
Well, that's one possible construction, but there should be more deformations than the ones coming from such things.
Yes, but how do you think about this in the abelian variety sense? I mean,
I'm not aware of any geometric constructions that should give something similar like that. That's an interesting thing to think of.
So we don't know what we get in this case.
No, I think in general we don't know what we get, but there I think I mean, I don't know any examples that I knew already a priori before the statement of the theorem. I guess that's what I'm saying. We do know what the period domain is, and it is what you would expect from somehow the older theory of Mukai on derived equivalences between abelian varieties. But yeah, whether the objects parametrized occur in geometry or in nature in other places is not immediately clear.
Sorry, could you just remind me, for either K3s or abelian surfaces, that kind of mysterious component, am I supposed to be probing the analytic, non-algebraic K3s or tori?
No, so, okay, so there's two different stories going there. So no. So if you want to do more like global deformation theory, so there's two stories that happen. One is the difference between formal deformations and polarized deformations, and that you already have just with commutative deformations. So the formal deformation space of a K3 surface will be 20-dimensional, but it will consist of only analytic or formal objects, and you'll have 19-dimensional subspaces of polarized things. And then this theory will give you two extra dimensions that a priori will also be purely analytic in nature or formal. So you get a 22-dimensional space. And now if you equip it with some stability conditions, and you can show that the deformation theory works well with respect to stability conditions, it will cut out something of codimension 2, so you'll get a 20-dimensional deformation space that should algebraize.
Yeah, so I was asking to not put any stability conditions on, like you did.
Then I guess you get something that's both formal and non-commutative, and not so much global you can say about it.
Okay, but just a priori, if I just have my family of analytic K3s, I can consider the derived categories of coherent analytic sheaves. On the algebraic locus by Gaga is the exact same thing. So it seems like those are giving me deformation directions. They aren't all of them. I agree with that. You still want to turn on Brouwer classes or something like this as well.
But yeah, so they will give you the deformation directions that you already see in just the formal deformation theory of your K3 surface. I guess that's what I'm saying.
Sure, it's just, okay, fine. It's the thing you're telling me about includes guys that I would have thought of as analytic.
Yeah, sure. So the answer to that is absolutely, yes, definitely. Yeah.
So that's all I wanted to know. Okay.
Yeah.
Any more questions? Okay, if not, let's.
Sorry, can I?
Yeah.
Do you have example where the this deformation space of the category is pro-representable by something that is non-smooth. So in the non sort of unobstructed case, do you sometimes get?
So the answer is I have, so only in interesting cases where you know that there are no non-commutative deformations. So where the entire second Hochschild cohomology consists of the H1x dx. In other cases, I mean, I really crucially need this kind of this lifting trick here, which really needs the unobstructedness. So without the unobstructedness, I have no idea, no way of relating the associated formal moduli problem with the actual thing you're interested in.
I see, thanks.
Like what about P2 or something, even that?
Ask me later. I don't think I'm going to give a meaningful answer on the top of my head.
Okay, let's thank Lenny again for the wonderful talk.
Thank you.